All right, here's our continuity homework video. We are going to evaluate the continuity of the function when is the function not continuous and what type of discontinuity is seen. So to figure out when the function is not continuous, we typically set the denominator equal to 0. So I have x squared minus 4x minus 12 equal to 0. I'll just put it right there. And to solve this quadratic set equal to 0, I'm going to factor. So find two numbers that add to get -4 and multiply to get -12. That's -6 and +2. And two solutions are 6 and -2. Now, removable, non-removable, how do we know? Well, we can either plug both of these in and figure out what's going to happen. But I'd ask you to also find the location of the non-removable discontinuity. Now, the easy way to figure out if we have removable or non-removable is if we plug the numbers back into the original equation. If you get 0 over 0, which you would, plugging in -2, squaring is 4, 2 times -2, that's -4, you'd get 0. I know the denominator, I'm going to get 0. 0 over 0, that indicates that at x equals -2, we have a removable discontinuity. If I plug in 6, I'm going to get a number. I know I don't get 0, I don't care what the number is, but I know I get a number divided by 0. That's an indication that we have a non-removable infinite discontinuity, or an asymptote. Okay? Now, let's find the location of the removable discontinuity. What we need to do is factor and remove kind of the preventative part that that doesn't allow me to plug in -2. This gets removed. I get a simpler function. It's different. It's going to be the same as the original function for all points except for at one location at x equals -2. And if I find, I don't want to call this f, I'm going to call this like a new f, like f2. If I plug in -2 into this new f, I get -2 over -8, which is +1/4. So I have x equals 6 is a non-removable asymptote, and then x equals -2 is a removable whole with location -2, 1/4. Okay, let's keep going. Set that equal to 0, factor out an x. I get x squared minus 9. I get back to this is the difference of squares. X plus 3, x minus 3. I get 3 locations where I don't have where I'm not continuous. It's 0, and -3, and it's 3. Now, let's look at the numerator. It's probably going to be easier if I had a calculator. I could just plug these values in, and it'd be quick. But I don't have a calculator, and you're not going to have a calculator or a quiz. So probably the easiest thing to do right now is to factor the numerator as well. And if I factored the numerator and put it under the factored denominator, I would start by factoring out a 2. I'd have x squared plus 5x plus 6. And then I'd factor that to be x plus 3, x plus 2. So I got 2x plus 3, x plus 2, and then the denominator is x plus 3, x minus 3. If I just turn our function into this completely factored form, it is easy to see which of our discontinuities are removable and unremovable. Now, what's important to do, this is very important, don't cross off these x plus 3's right away and not include this -3 as a discontinuity. In my original function, -3 is a discontinuity. It's just a removable discontinuity. So I would say this is removable. 3 and 0, nothing cancels, non-removable. Now the question is, what is the location of the removable? Well, my simplified function, f of x or g of x, so I'm going to say g sub 2 is 2x plus 2 over x times x minus 3. So I plugged in negative 3. I would get 2 times negative 3 plus 2 is negative 1. And then negative 3 times negative 3 minus 3 is negative 6. I get positive 18. So I get negative 2 over 18, which simplifies to be negative 1 over 9. So the removable discontinuity has a location of negative 3 comma negative 1/9. And just to remind you, if I asked you for both of these questions, instead of like having f of x, if I said, what is the limit as x approaches negative 2 for this? What it is essentially asking you is, what is the location of your hole? What is your y location of your removable discontinuity? You would answer this as 1/4, because that is what our function would be approaching. It's approaching this hole from the left and from the right. Here, if I asked you what is the limit as x approaches negative 3 for this question, for this equation, this expression, well, you would answer that it's negative 1/9. Your function has a hole at negative 3. The hole's location is approaching negative 1/9. All right, let's keep going. I'm just going to go ahead and factor the top and the bottom. So the top is going to factor to 4x times x plus 4. This will be the most efficient way to figure out our removable and non-removable discontinuities. X to the fourth minus 4 is a difference of squares, so I have x squared minus 2 and x squared minus plus 2. So difference of squares, we remember that if we have a squared minus b squared, it simplifies to be a plus b times a minus b. This is x squared being squared, and this is 2 being squared. So that's why I have x squared minus 2 and x squared plus 2. Now, what's interesting about this, after I factored the denominator, I see I actually have this, which can be factored. This is x being squared, and this is 2, root 2, being squared. So the denominator can be simplified to be x plus root 2, x minus root 2, and then x squared plus 2 does not factor. This is a sum of two numbers which cannot factor. There's no value for x that you could plug in and square and it to be equal to negative 2. So there's nothing that makes this denominator 0. My only two discontinuities would be at negative root 2 and positive root 2. I notice that I can't simplify anything, so both of these are non-removable discontinuities. So I don't have to find the location of a hole, thankfully. Let's look at this guy. We got cosine of x is equal to minus 1/2. Well, let's set that equal to 0. I'd get cos x equals positive 1/2. There are values between 0 and 2 pi where cosine is equal to 1/2. So I'm thinking about when the adjacent side is 1/2. That would be here at pi over 3. And down here at, that's 5 pi over 3. So pi over 3, 5 pi over 3. These, none of these things cancel. Nothing will simplify itself. So these are both non-removable asymptotes, vertical asymptotes. Let's look at this. Once again, this x squared plus 2, we cannot factor this denominator. There's nothing that will make this denominator 0. Since there is nothing that makes this denominator 0, I don't have to factor the numerator. I don't have to look at anything because we are continuous. There's no discontinuities. Why are there no discontinuities? Because you can't solve this. Look, if you subtracted 2, I'd get x squared is equal to -2. We will not have to worry about imaginary numbers. So we will not have to worry about square roots of negatives, plus or minus. You know, you could call this root 2i, but you don't have to worry about this. So this function is continuous. If you wanted to factor the numerators for practice, this would be x plus 11, x minus 2. We need to be prepared to factor these. There's different ways to factor it. You could either use any technique that you've learned in Algebra 2 or in pre-calculus, or sometimes they're going to be easy enough to just guess and check. You have just 2x squared. So that means the first terms, when you factor it, have to be 2x and x. Now for the denominator, I know I have to have a version of 3 and -1, either in here or there. So like -1 and 3, 3 and -1, in any of these locations. Now I'm going to think about how can I create something where I'm adding our two middle terms together to get this 1x. So that's why I'm thinking, okay, this should be a +3 and this should be a -1. Because I'd have 2x squared, this is me distributing everything. I'd have -2x, I'd have plus 3x after I distributed the 3x, and I'd have a -3. This turns into 2x squared plus x minus 3. That's what I wanted. So that's the factored form. Okay, in the numerator, let's think. I got to have a 5 and a 3 or a 15 and a 1. I'm thinking of 5 and 3. I'm thinking 2 times 5 is 10. And then plus 3 gives me 7. So that's why I picked 2x plus 3, because 3 times x is 3x. 2x times -5 is -10x. They will add together to get -7x. You can always check. There are other techniques to get these answers, to get these factored forms, but guess and check will work. But just check check by distributing. 2x times x is 2x squared. 2x times -5, -10x. 3 times x, 3x. 3 times -5, -15. Okay, that would simplify to be -7x. We're good. All right, great. Now, where are my discontinuities? When our denominator equals 0. So that's when 2x plus 3 equals 0. So that's subtract 3 divided by 2. X equals -3/2. And at x equals 1. That's when x minus 1 equals 0. Okay, so those are two discontinuities. I can tell right away that since this cancels, the 2x plus 3's cancel, that the -3/2 is going to be our removable discontinuity. 1 will not simplify. That'll be our non-removable. I can double check that by plugging in these two values into my original equation. If I get 0/0, we're good. If I don't get 0/0, it's going to be an asymptote. So here's our non-removable infinite discontinuity. Here's removable. Let's find the location of the removable. Well, our simplified L function, our L sub 2, is x minus 5 over x minus 1. I will plug in -3/2. -3/2 minus, I'm going to simplify this to be 10/2. We need to be able to work with fractions in an efficient manner. So if you are intimidated by this, you need to work, because we will not be able to use our calculator for our quiz coming up. We need to be able to say, okay, 5 is the same as 10/2. That's how I'm going to subtract fractions. I need the same common denominator. It's like having like terms. This will be -13/2 in the numerator. In the denominator, I'll have -5/2. That will simplify to be -13/2 times 2 over -5. The 2's will cancel. I end up with 13/5. So the location of my removable is -3/2, 13/5. Okay. Next two. All right, this is a great question, because for m, I'm using this piece for every single value except for 1 and at 2. All right? Well, if I evaluated just this piece, if I just looked at x minus 1, over x squared minus 3x plus 2. Well, the denominator can factor, and the denominator factors to be x minus 2, x minus 1. I know that this would have a removable discontinuity at x equals 1, so I have a hole at this, on this piece at 1. If I just looked at this piece, it'd have a hole at 1. At 2, I'd have an asymptote. Okay, so if I think about just graphing this, if I just graph this piece, I don't know exactly what it looks like, but at 1, I'd have a hole, but at 2, I'd end up having an asymptote. And maybe the function looks something like that. I'm not sure, okay? Well, if I have a point 1, negative 1, maybe this point actually aligns with my function and with the hole. Maybe I have a situation where my function that has a hole will line up so that the hole's location is filled in by the point. And if the hole's location is filled in by the point, the function is continuous at 1. I would not have a removable discontinuity. It might just be continuous. Now at 2, I have a point right here, but at 2, we have a non-removable discontinuity. So it might have a situation where we just can't be continuous at all. So I know at 2, we are not continuous. But let's check at 1. If I simplified x minus 1s, and I create this kind of like new function m sub 2 of x of 1 over x minus 2, and if I plugged in 1 into that, I would find that the location of my hole for just this piece is at negative 1. So this piece has a hole at 1, negative 1. This point fills in the hole. It is because of this reason we do not have a discontinuity at 1. We would just have a discontinuity at 2, and it would be a non-removable discontinuity. So that is a nice tricky problem that we need to be prepared to do. Discontinuity only at x equals 2, and it's a non-removable infinite. This function we need to be familiar with. You think at 4 we would have a removable discontinuity, because if I plugged in 4, I'd get 0 over 0, right? And for most situations that would be correct, but for this type of function, this is a special type of function. This is the only function that we are going to have to worry about that's not a piecewise function that has a jump. Because if we think about it, if I have x's that are bigger than 4, it's going to be like x minus 4 over x minus 4. Like if I plugged in 5, this stays positive, this will be positive, this simplifies to be 1. If I have x's that are less than 4, well, the top is going to be positive, whereas the bottom is going to be a negative value. This simplifies to be negative 1. So it turns out I'd either have positive 1 or negative 1, either to the right or to the left of 4. So x equals 4 is a discontinuity, but it's a non-removable jump. We need to be familiar with this function. Okay. Piecewise functions find a and b such that x is continuous. Well, for these two examples, just to start off with, I know this piece is going to be continuous. I know this piece is going to be continuous. It doesn't have denominators. We cannot set the denominator equal to 0. So all I need to worry about is making sure that this piece meets up with this piece. I would be using the ax squared minus 2 until negative, I'd use the ax plus 3 from the left of negative 1. So I'd have some sort of line until negative 1. I need to make sure it meets up with this quadratic so that things are continuous. So all I need to do is make sure that this little guy, I'll call it f little 1, meets up with f little 2 at negative 1. Now I'd have a times negative 1 squared minus 2 equals a times negative 1 plus 3. This is a minus 2 equals negative a plus 3. I'll add an a to both sides, I get 2a. I'll add 2 to both sides, I get 5. Divide by 2, a is equal to 5/2. Okay? This guy, well, this line needs to meet up with this line at 1. This line needs to meet up with this line at 3. It's not too difficult so long as you understand the domain and how we're using this piece until 1, but I start with this piece at 1. So let's start with f little 1 at 1. Needs to meet up with f little 2 at 1. This will be 1 plus 1, which is 2, equals a times 1 plus b. Okay, so I get 2 equals a plus b. There's one equation, and this is at 1. Then the second piece at 3 will need to meet up with the third piece at 3. So f little 2 at 3 will need to meet up with f little 3 at 3. Now, plugging in 3 into the second piece, I get 3a plus b. Plugging in 3 into the second piece, I get negative 6 plus 6, which is 0. So now I get another equation, 3a plus b equals 0. When you have two equations and two unknowns, mostly in this class, it'll be easy enough to set up and solve using substitution. Since I just have one b here, I'm going to solve this equation for b. Solve for any variable and substitute it into the other. This I can turn into 2 minus a equals b. I'll take that, plug it in here. I get 3a plus 2 minus a equals 0. That's 2a plus 2 equals 0. 2a equals negative 2. A's got to equal negative 1. I got a. Now that I have a, use either equation to find b. Let's use this one because it's easy. 2 equals negative 1 plus b. B's got to equal 3. Okay? And that is how I find a and b when I have a system. All right, more of the same. First piece needs to meet up with the second piece at 0. I'm plugging in 0 in for x, not for a, because it's when x equals 0, when x equals 0. Cosine of 0 is 1, so I have 1 plus a equals negative 4a. Subtract an a, I get 1 equals negative 5a. A's got to equal negative 1/5. Another system. First piece meets up with the second piece at 1. Second piece needs to meet up with the third piece at 2. Let's create our equations. I got a times 1 squared, that's just a, equals 2x plus b, 2 plus b. Next one, I'll have 2 times 2 plus b, which is 4 plus b, equals 2 times b plus 1, 2b plus 1. Second and the third equation just has b. I can solve for b. That's easy enough. b is equal to 3, subtract 1, subtract b, plug that back into this equation to find a. A equals 2 plus 3, a is equal to 5. Now, these are whole numbers that we've, worked with. Please don't be afraid if you see fractions when you're doing these problems. All right, another one. First piece meets up with the second piece at 2. I get 4 minus 3a equals 8 minus a. Add an a, negative 2a, subtract 4, I get 4, a is equal to negative 2. Another one, just making sure we are used to different forms of variables and plugging in there. Let's say this is the first, second, third. First piece needs to meet up with the second piece at negative 1. Second piece needs to meet up with the third piece at 2. Now, when I plug in negative 1 into my first piece, let's make sure we remember what to do with a negative exponent. 2 to the negative first is the same as 2 to the first in the denominator. So this is the same as 4 times 1/2, which is the same as 4 times a half, 4 divided by 2, which is 2. Okay, so negative exponents is the same as the positive exponent in a reciprocal. Second piece, plugging in negative 1, I'll get negative a plus 2b. So 2 is equal to negative a plus 2b. So the second piece and the third piece need to meet up at 2. Plugging in 2 in for x, I have 2a plus 2b equals 3 squared minus 2. 2a plus 2b equals 9 minus 2, which is 7. All right, I'm going to solve for a variable. The easiest variable to solve for is going to be this a over here. I solve for a, I get add an a, subtract the 2, a equals 2b minus 2. I will then plug that into this equation, giving me 2 times 2b minus 2 plus 2b equals 7. I think now I'm going to deal with some fractions. Let's see. 4b minus 4 plus 2b equals 7. 6b minus 4 equals 7. Add 4, 6b equals 11. Divide by 6, b is equal to 11 sixths. Once I have what b is equal to, I can solve for a. We need to be comfortable with fractions. We already have a solved for. A is equal to 2b minus 2. So a equals 2b minus 2. This turns into 11 thirds. Okay, that's 22 sixths divided by 2. It's 11 thirds minus 2. 2 is 6 thirds. 11 minus 6 is 5. So a is 5 thirds. So that's my answer for B and for A. All right, back to the whole situation. If I just looked at this piece, because this piece is used for everything except for one point. Well, if I looked at this piece just in general, I would realize that after factoring, that this has a removable discontinuity at x equals 2. So this piece has a hole at 2. So if I graphed like just the first little piece, f sub 1, it's going to have a hole over or under 2 somewhere. I need to make sure this point fills in the hole so that my function is continuous. To do that, I need to find the location of the hole. So, how do I find the location of the hole? I will simplify the x minus 2's, and I will plug in 2. This is like even a separate one, like f little 1 star at 2 is going to be 2 plus 2, which is 4. So this is the y location of the hole. Well, this second piece has to equal the first piece's location of the hole. The second piece at 2 is 6 plus b. The location of the hole is at 4. B's got to equal negative 2. Okay? Cool. What we essentially did there is find the limits as x approaches 2. I have a hole. I can simplify to find the location of the hole. Same deal, I'm assuming. F little 1, I bet, has a hole at negative 3. Yep. We have a removable discontinuity at x equals negative 3. Let's find the location. So I'm going to turn this into f little 1 star because I'm going to simplify the x plus 3's, and I get x plus 2. Well, the first piece that has a hole at negative 3, I got to fill that hole with this point. So f1 star at negative 3 equals negative 1. f1 star, the hole's location, must equal my second piece's location, my second point's location at negative 3. So the hole's located at negative 1. We have an x equals negative 3. We can solve for a. I'll add 3. I get 2 is equal to negative a. Divide by 1. A is equal to negative 2. Okay? Fantastic. Explain using words in a diagram the meaning of an intermediate value theorem. I'm not going to write down the words. I'm just going to use the diagram. Intermediate value theorem says if the function is continuous, and it's got to be continuous, I guess I'm using words, whatever. And I got 2 points that I know exist on the function. I must cross through every single one of these y coordinates at least some location, at least one location between these two x coordinates. There's got to be a point where we have an input that gives me that output and that output. Because no matter how I connect these two pieces, no matter which way I decide to connect them, I will have to cross through all those y coordinates. This is why if I have a negative y coordinate and a positive y coordinate for two x coordinates, I know I got to cross through 0 at one location. I might not want to, but I'll have to if the function is continuous. So that's the intermediate value theorem. We got 2 points. You got to cross through all of the y coordinates between those 2 points at some x value. Okay? It is this theorem that will help us show that there are solutions for certain equations, like this function equal to 4. Now, if I try to solve this equation, I'm not going to have a good time. This is not something that is solvable by hand. We can use our calculator to solve it. But I just want to show that there is a solution somewhere between 0 and 3. Okay, well, first thing I need to note is that this is continuous. Since it's continuous, the intermediate value theorem applies. And it just needs to be continuous on my interval from 0 to 3. I then find the 2 points that I'm interested in. Well, f of 0 is -2. F of 3 is 27 minus 9 plus 3 minus 2. So that's 18 plus 3, 21 minus 2, 19. That means on this function, I have 2 points, 0, -2, and 3, and this is not going to be to scale, 19. I have to connect these 2 points somewhere. I must pass through y equals 4 at some location. So you'd say, since f of x is continuous and f of 0 equals -2 and f of 3 equals 19, there must be an x between 0 and 3 such that f of x equals 4. That's what you would write. Show this function as a root. You got to understand what a root is. A root is a 0. So, show that this function has a 0 somewhere between 2 and 3. We're talking about g here. So, g's got a root somewhere between 2 and 3. So, g of 2, let's see what that is. Well, first of all, I know this is continuous. Okay, so continuous, that's important. There's no denominator. Obviously, it's continuous. I plug in 2. I get 8 minus 12 plus 3. That's -4 plus 3. That's -1. 3. 27 minus 27 plus 3. That's 3. Okay. Again, I'm not going to try to solve this. It's not going to be something I can do by hand. Okay? Maybe it is. In this case, it's not. But I do know that I have the point 2, -1, and 3, which means I must cross through y equals 0 in at least one location between 2 and 3. So I'd say since g of x is continuous, g of 2 was -1, g of 3 was 3. There must be an x between 2 and 3 such that g of x equals 0. Same deal, pi. At least once. I didn't even give you an interval. Well, I don't know, let's mess around. What's 0? F of 0, e to 0 is 1, plus 0 squared, it's 1, okay? What's f of 2? Is e squared plus 4 bigger than pi? Yeah. So, I have 2 points, 0, 1, and 2, something larger than pi. This doesn't have a denominator. It's never going to equal 0 in the denominator. It doesn't have any discontinuities. This is continuous. So I know somewhere between 0, 1 and 2 e squared plus 4, I have some solution where this is equal to pi. Am I going to try to solve this equation set equal to pi? No. The intermediate value theorem just guarantees the existence of said solution. So since, and here I'm just going to pick 2 x's that I'll say straddle y equals pi. And I, easily pick 2. Since f of 0 is 1, and f of 2 is pi, and f of x is continuous, I forgot that. There must exist an x between 0 and 2 such that f of x equals pi. All right? And that's it. There are some situations where you have to actually find the solution, but didn't ask you to do that here. All right, that is the video, and this is the key. I hope we understand the concepts of how we are actually finding limits. We are finding locations of holes without using our calculator, and we are understanding when we have removable and non-removable discontinuities. Non-removable typically being infinite, except for very specific situations where a non-removable discontinuity is a jump. Okay? Thank you. I gotta stop the video. I'm trying to upload it to YouTube, but I haven't even stopped it yet.